So in this class, you should be able to learn how CFD impacts the design process in general of a product. Then for those who have never used Autodesk CFD, they will have the opportunity to discover the user interface and a typical workflow of setting up a turbomachinery model. Then the most exciting part will be that you're going to learn how to use the post-processing tools offered by Autodesk CFD to interpret your simulation data or results and make decisions after that. Our presentation is going to be composed of mainly 3 sections. For the 2 first sections, we're going to see the impact of CFD on the design process of a product in general, and then more specifically on a turbomachinery model. Then we will go together through an exercise for setting up a centrifugal pump as a turbomachinery application in Autodesk CFD. For the 4th section, you're going to be able to ask questions where I'll be very glad to answer. By the way, it's going to be a discussion. You can ask a question wherever you want. So, a typical design process of a product is composed of many steps that goes from the first concept till prototyping and testing. But during this process, manual calculations are involved. The problem is when you go from manual calculations till prototyping and testing, you need a lot of time and money because you need to create a prototype and prepare the test bench. The problem is during this process of from manual calculation till prototyping, design failures may happen. This is a big problem because you will need further efforts of rework and fix. So you need to reloop again to the manual calculation and create the prototype and prepare the test bench again. So it's gonna be, you will need like months or sometimes years to be able to get the final prototype. I'm really curious to know from you if you have an idea how does traditional design process of a turbomachinery model, starting from the first concept to prototyping and testing, how much time does it take? Sorry? I mean, the traditional design process. It's like with hand calculations. I'm asking you, I don't have the answer, so I want to like discuss it with you. I would say years, yeah. Okay, thanks. On the opposite side, for a modern design process, leveraging CFD earlier in the design process helps you avoid this further efforts of rework and fix. You will save a lot of time and money because CFD calculation, the CFD software allows you to create as many designs as you can, many scenarios where you can define many input conditions, different geometries, and then you can compare between them. You can get the performance of each design. By the way, Autodesk CFD creates automatically for you the performance curve for each pump, so you can make a decision and say, okay, this is my virtual prototype which is ready. It's matching the expected results. I'm going to jump directly forward to prototyping and testing. This is simple. So now we will dig into the loop of the CFD calculation. What does it happen inside to see how we create this virtual prototyping? Actually, the CFD calculations impact the turbomachinery models in a way that you can extract simulation data. What does it mean? It's the ability to predict performance, to see the impact of modification of a design, to chase opportunities for improvement. The result visualizations that CFD offers allows you to capture flow features inside your model. So you can see problems of the flow inside the model. The flow can show you recirculations area, flow separation, or high gradients of pressure and velocity. This is very important to say, okay, I see where the problem is. I'm going to improve my design and see what's the impact. Now, we will work on setting up a centrifugal pump in Autodesk CFD. Why I chose to work with the centrifugal pump? Because it's the most common used turbomachinery application in Simulation CFD. What is a centrifugal pump? So it's mainly composed of two components, a rotating device called an impeller and a static device called a volute. Each one of these components has different designs, geometries, and shapes. In CFD, you can play with them. You can juggle between the different geometry, combine them, and then run them like at the same time, and then decide what is the best performant model. And if you have, or if you are running on the cloud, you should be able to run 20 simulations at the same time and get the results. So, before I explain how does a centrifugal pump work, I want to ask you a question. Do you know what's the difference between a turbine and a centrifugal pump, knowing that they have the same, exactly the same geometry? Sorry? Almost, correct? Exactly, this is true. So a turbine, the impeller of a turbine is not working, it's not rotating. It's rather flow driven. So the flow passes through the pump and then the impeller rotates. So it's mainly converting kinetic energy from the fluid to mechanical energy of the impeller. On the other side, for the centrifugal pump, it's the other way. The impeller rotates, so its mechanical energy is converted into the fluid as kinetic energy. So the centrifugal pump are mainly used to raise pressure or to drive flow in a controlled volume. So the working of a centrifugal pump is very simple. So the impeller rotates. It creates a low pressure at the inlet. This low pressure helps suck the fluid surrounding it. This fluid is pushed radially through the blades passage of the impeller and then discharged till the outlet of the pump. It's very simple. Mechanical energy, kinetic energy, and then out. So here's a model I simulated in CFD. The colors that you see on the impeller, it represents the pressure. The streamlines represent the velocity. The blue color is the lowest value, and the red color is the highest value. So you can see that in the sucking section, in here, pressure is low, and then it increases on the blade tips. So this is our goal today. We're going to work together on the best practices to see how we get this. First, I want to remind you of a typical workflow of CFD. It's mainly composed of 3 steps: pre-processing, processing, and then post-processing. Pre-processing, it's input. Just in a word, it's input. processing, it's solving. And then post-processing, it's the output you're trying to get. We will start together by the first step, which is the post-processing. The first phase in this post-processing is the CAD model. For this phase, we need to do it in the CAD software, not in CFD. But first, we need to make some modification on the model, on the raw data of a CAD model, before transferring it into CFD to avoid having meshing problems. So one of these simplifications are to remove the small gaps, because the small gaps may be problematic, as you need to create more mesh for them. And if you create more mesh for them, you're going to have a huge mesh, while the small gaps doesn't play anything, doesn't give any additional value to the final results. Also, we have to remove also some useless features. For example, the region of air here, trapped between the impeller and the volute. As the impeller rotates, we're going to be interested only on the flow around the impeller. This would stay static, so it wouldn't bring anything, so we just delete it. Here, it's the CAD model. We got it from the manufacturer, the raw data. And this, after cleaning up the model, we removed the gaps, the useless features, and we got rid of the very small gaps on the other side. We finished the CAD model cleanup. We will create a rotating region. The rotating region is a default material in Autodesk CFD. It enveloped a rotating device and a part of a fluid. So there is a rule to create the rotating region in the CAD software. You need to make sure that it's positioned halfway between the wall of the volute and the impeller. Sometimes you have a case where the impeller touches the wall of the volute, like in here. No problem. The rotating region does also the same. Even if you have a very small gap between the impeller and the wall, you should close the gap, and the rotating region should also touch the wall of the volute. The third and the last step in the CAD model cleanup or preparation is to extend the openings. We need to make sure that we extend the inlet to have a fully developed flow, and then to extend the outlet to make sure that we are avoiding recirculations that may lead to mass balance issue in our model. We're done. So now we're going to move to the live demo. We're going to transfer this prepared CAD model into Autodesk CFD, where we're going to define the materials, solid, fluid, and the boundary conditions. That means our input data, and we'll mesh it. And then we will launch it to the solver. To do this kind of analysis, you really need to have a motion solver. The advanced or basic solver wouldn't allow you to run this kind of analysis. Amy, can we switch to the live demo? Okay, good. So this is CFD, and we are under the setup tab. We need right now to define the first step and the setup, which is defining the materials. So here I already defined the fluid parts. You just need to select them and then click Edit, and then you have a rich library of default materials. You can choose one of them. You can choose even, for example, blood, and then apply. You can run simulations with blood flow. So I'm going to put it back to water. And then you select your solids. and then choose also the type of material solid. You have also a rich library. You can even select a human if you think that it's a good idea to simulate it in this kind of analysis. And yeah, glass, a lot of default materials. You can also create your custom materials, by the way. So I'm going to put it as solid. And then the third part would be to define the rotating region material. So you define here the axis of rotation. That means like where the flow is going to pass through the impeller. And then under the properties, here define the name. And then for the properties, you have in CFD 3 scenarios. It's either you give a known rotational speed, or a driving torque, or a free spinning. That means a flow-driven impeller. For our case, we're going to concentrate on the known rotational speed because it's the most used scenario from our customers. So for the rotational speed, you really have to make sure that you ramp up these rotational speeds. A best practice is that we noticed that when we ramp up rotational speed over 50 times step size, it's more stable and give more accurate results. So this time should be 50 times step size, then multiplied by the step size. This time step size is calculated automatically according to the value of the rotational speed. Okay. Then everything is on here. We will move to the boundary conditions. For the boundary conditions, at the inlet, I defined a pressure equal to 0 and a mass flow rate. The mass flow rate also, or a non-zero pressure, should also be ramped up exactly like the rotating region at the same time. So here I used a piecewise linear curve. And then probably you're going to ask why I specified a negative value. It's simply because the orientation of the arrow, just to make sure that it's pulling flow out. So as you can see, it's ramped up exactly like the rotating region. Okay? And then now the meshing. For the meshing, we need to make sure, because here in this case, we're running flow-only simulation. We're not running heat transfer. So it's a good practice to suppress the solid materials because they're going to just add more mesh elements to our model. What doesn't mean to suppress solids is not to mesh them. There is an option in CFD where you can click on a material and say suppress, no mesh. So I suppressed the external volute and the impeller. The most important regions that you have to take care of when simulating rotating region analysis are to refine the leading and trailing edges of the blades of the impeller, because they are the regions where high gradients of velocity and pressure happen. A second region is the volute tongue, because here does happen flow separation as the flow leaves the impeller to the volute. Sometimes it's a good practice also to create mesh refinement region. On this location, you just need to adapt it to this location to be sure that this region is well refined. So, another important point is that we need to make sure also that the rotating region is uniform. The mesh is uniform, because we need to have the same flow that goes on the inlet and outlet the same. We don't have to have more flow on this side than this side. We should uniform it. this is very important for the stability of the simulation and for the accuracy of the results. If you need more details, please download the document. It's very useful. So here I'm going to run transient. As you can see here, the time step size depends on the value that you give. We recommend usually to have 3 degrees per time step as a start. You give 3 and then you calculate, you're gonna get the time step size, this one. You multiply it by 50 and go back again to the rotating region and to the boundary condition of the outlet to ramp them up. Here I chose to work with the number of blades. That means that it goes from blade to blade to the rotating region. So it should be 360 degrees over divided by 8 should be, how much is it? 45 degrees per time step. So then, a very important thing is to correctly set the turbulence model. For high-speed rotating devices, we recommend to use the SSTK-omega. And more better is to use the SSTK-omega RC. It's proven that it predicts well the pressure drop and it captures well accelerated flow over convex surfaces. So I used the R SST, and then we need here to select some variables. So by default, CFD has the variables velocity, pressure, temperature, density, wall heat flux, and shear stress selected. Then if you want to see further values, you just need to turn them on here. So I need here the wall model Y plus value, because when using the turbulence model, we need to capture well the flow near the wall. So we have to make sure that the Y plus value is around 1. The stream function does give us information about the nodal aspect ratio. So the nodal aspect ratio does give us the information about how bad or good the mesh is. So a bad value of the nodal aspect ratio is around 1,000, and it refers that our mesh is in some regions very bad. So we have to improve the mesh by refining it or changing the geometry. The save intervals is an option for the ones who are interested in creating animations. You can save, for example, each 5 seconds the simulation. You say, okay, I'm going to capture the results every 5 seconds, and then you can see the animation after that. Or you can say that I want to capture the simulation every 10 steps. It depends on what you need. Finally, before launching the simulation, I want to show you a very important flag that we added for the version 2018 of CFD is the ADV5 no D time. You use it, you turn it on when you're using Advection Scheme 5. And this flag is very important because it improves the stability of your pump if you are having a pressure equal to 0 at the inlet. So to solve, you have 3 options. Locally, scalable solver, it's done for high computing devices and for models that are from 10 to 15 million mesh elements, or on the cloud. And then we hit solve. We are done with the setup. Amy, can we switch back again to presentation? Amy? I think the lunch was very good. So I want to remind you here of the most important things that you really need to avoid when setting up your model. So you need to make sure to ramp up your rotating region, because if you don't ramp it up, you will have instability and sometimes divergence of the simulation. The same for a non-zero pressure and a flow rate at the outlet. Because if you say, okay, I'm going to define a constant flow rate at the outlet, you will have a reverse flow at the beginning of the simulation. And probably this will cause divergence. If not, then you're lucky. For the meshing, you really need to define an adequate mesh. It's very important, especially that you need to uniform the mesh and refine it in region of interest. The volute tongue, the leading and trailing edges of the blades of the impeller. Because the rotating region analysis are very mesh sensitive. A second point is to make sure that you're suiting the SST K-omega model that says that you need to have a Y plus value around 1. A best practice is, so in general, for the SST K-omega model, you have to have a number of layers between 5 to 10. And a good practice also, and then you tweak between the layer factor and layer gradation till you get the Y plus value that you need. And a very good practice is to turn on surface refinement in the mesh, because it helps smoothen the transition between the wall layers and the local mesh inside. And it also helps smoothen or helps like the growth of the elements, not only on the edges, but also on the surfaces. So it really refines very well the mesh over the surfaces. While working on a model, I created the rotating region very close to the impeller. And the problem is I forgot to make it uniform. So I got this. I got pressure, hotspots of pressure, high gradient pressure region, just on the rotating region near the blades of the impeller. And the convergence the simulation was very unstable. I wasn't able to get convergence at all. Everything was oscillating like crazy. So please make sure to refine the mesh and make the rotating region uniform. So here, as you can see, I wanted to show you, while I was working on CFD 2017, because we didn't have this flag before, I was running the model, and then I thought that everything is fine. Then I discovered that I have instability over the inlet where I defined pressure equal to 0, because simply I didn't have this flag who's helping the stability of my flow. So this is very useful for the ones who are running turbomachinery models. So the final steps is the result visualization is colors. In opposite to steady state analysis, a very good rotating region analysis should have this convergence plot that has the periodic aspect. But probably you're going to ask, but how can I assess convergence in this case? Simply by following the pressure. As you can see, as the simulation progresses and it reaches convergence, the pressure of velocity flatten out. Or you have other options. For example, you can create a monitor point at the outlet of the centrifugal pump and then track the values, the variables of interest, for example, pressure and velocity. They should flatten out as the simulation converges. You can also choose to create a monitor point on the inlet. It depends. It's up to you. And the third option is to extract the hydraulic torque values from the automatically generated rotating region file. You can extract the values of the hydraulic torque and then plot them against time. This value flattened out as the simulation convergence. So you have to choose one of them. It's up to you. You can even choose all of them and see how good is your results. So now we're going to see the tools that we use to extract simulation data. There is a very useful tool called the bar calculator. It's very simple to use. So you just need to create a cut plane. For example, you choose at the outlet, and then you say, okay, I need to see the values of velocity, pressure, temperature, density. And then in less of 1 second, you click calculate and you get all your values. It's very simple. For example, another thing or another tool is you say, okay, I want to calculate my pump efficiency to see how good is my pump. You create a cut plane over the outlet. You get the values of volume flow rate, pressure rise, and then plus you take the hydraulic torque values from the rotating region file, and then you calculate your pump efficiency. Now, we're going to move to the tools that we use to visualize results. They are very awesome. I like them because it's like everything moving, everything is colorful. And you can see all the problems in your model, very simple. So the cut planes, if you create a cut plane and then add vectors, you can see regions of high gradients of velocity, pressure, or even if you're simulating heat transfer, you can see the temperature change. You can see also regions of flow separation as the flow goes out of the impeller and then go to the volute, or even recirculations, as you can see there. You can also use a second tool, which is the isosurfaces, or there is also the isovolumes. I'm going to explain what's the difference. So the isosurfaces are used to find region of interest, like the cut planes, heist flow, or cavitation. What does it mean, cavitation? Cool. It's when the water pressure goes underneath the vapor pressure. Cool. Smart one. Then you can also find the regions where the mesh is bad by looking at the variable nodal aspect ratio. When creating an isosurface, you just need to define the quantity, that means the variables that you want to see, and color by, it's either you color it by another variable, or you see, I'm going to choose, for example, the same, like velocity, velocity. Isovolumes, for example, for isosurfaces, if you define here, for example, the quantity velocity, you say, okay, I'm going to see the isosurfaces for the values of 4,000 here, millimeter per second. For isovolumes, you have an interval, a minimum and a maximum. I want to see the isovolume between a range. So here's an animation I created while using isosurfaces, and it's not working. It should turn. It should rotate. Okay. Yeah, cool. So this is with isosurfaces here. The isosurfaces and the impeller are colored by pressure, and here the cut planes is colored by velocity. Finally, I want to share with you some points that, or a list of points that you need to go through if you are getting inaccurate results. For example, you say, oh, sorry, Amal, I wasn't able to get accurate results, or I didn't get the results that I expected from hand calculation or from experimental results. So I would say, go through these points and then come back to me. They should help you. So please verify that the geometry represents the actual geometry. Some users go further with the cleanup of the model. They simplify, simplify, simplify till they change the model totally. This should be really avoided. Then make sure to extend the openings when needed to avoid having the recirculation at the outlet, which leads to mass balance problem. Then verify that the input data are correct. That means you're giving the right RPM, the right input conditions at the openings, pressure. So you are matching also the experimental results. So make sure that the inputs are the same, and then let's see how the output look like. Then, as we said, we really need to make sure that we have a good refined mesh, because the rotating region analysis is mesh sensitive. And then finally, verify that the torque, pressure, and value have reached steady state. As I said, you need to run through these options. Either extract the hydraulic torque values, or use monitor points, or track pressure. If you didn't catch that these variables did reach a steady state, run further time steps. Now it's your turn. Sure.
I see when you're defining the pump, you can define the material of the pump, like aluminium or something.
We're just going to bring the mic over. And then anyone who wants any questions, just use the mic.
Thank you. I see that you can define the material of the pump, so like you put aluminium or steel for the pump, but can you actually play around with like the surface roughness?
Yeah, sure.
Oh,
There is a list of properties that you can create, for example, your custom materials, and define the properties that you need. Among them, there is also the wall roughness.
Ah, awesome. And I saw blood was included in the list of fluids. Blood's non-Newtonian. Does it handle non-Newtonian fluids?
Sorry?
Does it handle non-Newtonian fluids? So
Yeah.
that's amazing.
Yeah. I have some customers who use fluid.
Yeah,
rotating
for
region.
medical.
Yeah.
That's awesome. All right, thank you.
Cool, thank you.
Thank you. One question over here.
For this application, did you have to go into the motion tab to set anything there?
You can, but motion will need a lot of time to run first, and rotating region are more stable. I would advise you, if you're in a situation where you say, I have a Turbomachinery model, but I don't know if I run motion analysis or rotating region analysis, I would say if your impeller is symmetric, so go with rotating region. It's proven that it's more accurate and solves faster. You can ask anything, even not related to this topic. It's your opportunity to ask technical support live.
Any more questions? Yes, right at the back there. I'll just bring you over the mic. Actually, if that's the pass.
Hello.
you have set up the pump in that way. Is it a way of importing from other Autodesk applications the exact setup from Inventor or something that's either given by a third party or a vendor and bring the exact pump that's been used in an existing application?
So you mean you have a model in Inventor and you want to export it into CFD?
Yeah, bring it in and just run as many different things. You're not designing something, you're just having an investigation as to how it reacts to, yeah.
Sure, and we have a direct button, an add-in in Inventor, where you can click on it and it transfers the model directly into CFD. You don't have to export it into other file extension.
Thank you.
Mm-hmm.
Any more questions? Yes.
Is there any file size restrictions for importing the file to CFD? The size of the file, for example, a step file?
Yeah, the results are, for example, no, there is no restriction. For example, I had to run a model with 20 giga.
Okay. Okay.
Thanks. In stress analysis, when you're making a mesh, it's not so important to have a uniform mesh. Sometimes you want to concentrate the mesh in areas of interest. But you said that it was really, really important to get a uniform mesh in the rotating region. Why?
To make sure that on all the surfaces,
yeah.
you have the same flow, a uniform flow.
Yeah.
You don't have more flow in here rather than here.
Right.
You have to make sure that that goes in and out is the same on all the surfaces.
Okay. Okay.
Any more questions, ladies and gents? No? Okay.
Cool. Thank you very much.